Let's do an example with physical pendulum. Remember, the difference between a physical pendulum and a simple pendulum is a simple pendulum is all the mass is at the end of the pendulum, and a physical pendulum is one where the mass is distributed along the length of the swinging object. So an example of a physical pendulum is your arm swinging from your shoulder as you're walking, and an example of a simple pendulum is some big mass suspended at the end of a string of negligible mass. So let's do an example with a so-called physical pendulum. I kind of hate that name. They're all physical. They're all real pendulum. This one is from the book, chapter 14, number 33. It's a 3-bar problem. Several studies using cadavers to determine the moment of inertia of human body parts by letting them swing as a pendulum about a joint. It's a little bit macabre, but we'll work out the physics on it. So in this one, the center of gravity of a lower leg is 18 centimeters from the knee, and when allowed to swing, the frequency is 1.6 hertz. What is the moment of inertia? Oopsie, not inertial, inertia of this lower leg. Okay, well, for a physical pendulum, we have an expression for the frequency. Remember, for a simple pendulum, F is 1 over 2 pi times the square root of, what is it? G over L, I think, right? G over L. And for a physical pendulum, F is 1 over 2 pi times the square root of mdg over I L. Let me just make sure I did that right. mgd over I. There is no L in a physical pendulum. mdg over I. So we're given the frequency of 1.6 hertz. We don't know the mass, and we don't know the moment of inertia, which we have to figure out. We do know G is 9.8, and we know D is the distance of the center of gravity from the pivot point is 18 centimeters, which is 0.18 meters. Let's make a sketch, and I'm not going to try to make it anatomically faithful. Here's our pivot point, and I'm just going to draw the leg as a cylinder, basically. The problem didn't tell us to treat the leg as a cylinder or anything that way, but we're going to model it that way. And let me just make sure I'm not leaving out some essential piece of information from the problem. Oh, they do give us the mass. Well, that makes things a lot easier. M is 5.0 kilograms. Okay, that makes life much, much easier. We don't need to actually model the moment of inertia in any particular way. This just becomes very much a plug and chug kind of problem. I don't know why it's got 3 bars, because this is kind of a 1-bar problem. We've got F, we've got M, we've got D, we've got G, so we know everything in this problem except the moment of inertia. Let's crank through this one and do another one. 1.6 hertz is 1 over 2 pi times the square root of m dg over I. Let's rearrange that equation so it's I equals something. I'll follow my own advice and not put any numbers in until we're actually got answer equals what we want it to be. So 2 pi f is the square root of mdg over I. Square both sides and rearrange it. I get mdg over I is 2 pi f squared. Now cross multiply by I and divide by 2 pi f squared, and I get I equals mdg over 2 pi f quantity squared. That then just becomes, as I said, a plug and chug problem. Print m is 5 times 0.18 times 9.8 divided by 2 times pi times 1.6 all squared, and we get the moment of inertia of 0.87. And the units are kilograms meters squared. Moment of inertia is in mass times length squared. Well, so that's the answer to that problem. It's not very interesting. Let's do another problem that's maybe more interesting from chapter 14. Let's do let's do number 34. We did number 33. Let's do number 34. So this is chapter 14. Number 34. It's another 3-bar problem, hopefully more interesting. A child on a swing set swings back and forth with a period of 3.3 seconds and an amplitude of 25 degrees. What is the maximum speed of the child as she swings? So this is a pendulum, a simple pendulum problem. So there's like a chair here, and there's a child sitting, going back and forth like that. The length of the pendulum, we don't know. We know that the period, though, is 3.3 seconds. And we know that the amplitude is 25 degrees. So for a pendulum, the amplitude can be measured in terms of degrees or physical distance. And the question is, what is Vmax equal to? That's our question, not what's the length equal to. Well, the maximum velocity for something in simple harmonic motion is just a times little omega, which is a times 2 pi f. And so the frequency is 1 over the period t, so that's 1 over 3.3 seconds, which is 0.30 hertz. So we have the frequency. So to get the maximum speed, we just need the amplitude. We've got the amplitude, but we've got it in degrees, and we need it in meters. So what we're going to do is figure out what that amplitude is in length rather than in angle. So here's our simple pendulum. It's at 25 degrees here. It has some length that we don't know, and we want to get this S max, which is the amplitude, when the swing is at a 25-degree angle. Well, remember that S is L times theta when the angle is small. 25 degrees is maybe getting up there a little bit, but we're given this problem as a simple pendulum problem. We're treating it as simple harmonic motion, so that's what we're going to work with. So I can get the amplitude is L times theta max. I know theta max in degrees. I would need to convert that to radians. You never do any multiplication of an angle in degrees, always in radians, always in radians. Um, and so I can get my amplitude if I figure out what L is. Well, I can do that because I know that T is 2 pi times the square root of L over G. And I know T is 3.3. So seconds. So I can rearrange this. That gives me the square root of L over G is T over 2 pi. I square both sides. That gives me L equals G times T over 2 pi squared. So I put my numbers in for that. 3.3 seconds, 9.8 for G times 3.3 over 2 pi squared, and I get that the length is 2.7 meters. Then A is 2.7 meters times theta max in radians. So I have to convert 25 degrees to radians, which I do by multiplying by pi divided by 180. There's pi radians in 180 degrees. So print, and I get 0.436 radians, 0.436. So the amplitude in meters is 2.7 times 0.436 is 1.18 meters. And then Vmax is 1.18 times 2 pi times 0.3. And we'll squeeze it on this one last page. 1.18 times 2 times pi times 0.3 is 2.2 meters per second. Okay, so the way we worked through this problem, made a sketch of it, identified what we know and didn't know. That told us that in order to get what the question is asking for, which is the maximum speed, we needed to figure out an amplitude in meters, and we worked through to get the amplitude in meters from the amplitude in degrees by converting it to radians and figuring out the length of the pendulum from the period.